comes to analysis of variance, it's really what you, if you ever are going to be doing any statistics, this is the classical thing that most research uses. Class analysis of variance is very common. T-tests are common too, but analysis of variance is what is typically done. And what we just learned about is something called a one-way analysis of variance, or one-way ANOVA. So what we just did was a one-way ANOVA. What does one-way mean? Is there anybody who read the chapter? Can anybody tell me what one-way means? Or even look it up now? One-way ANOVA. That's a good guess, but that's not exactly it. One-way ANOVA means you are looking at one variable with multiple levels. The variable here, when we were looking at this example we just did, what was the variable? What was the independent variable? What did we manipulate in a way? We were looking at satisfaction as the dependent variable. What was the independent variable? Exactly, the department. So the department, or the affiliation, department affiliation was the, and we looked at 4 departments. Department affiliation was the independent variable, and the dependent variable, meaning this is what we manipulated and this is what we observed and calculated, was satisfaction, or whatever it was. Was it satisfaction? Satisfaction. And this independent variable had 4 levels. So what we did is we took 4 levels, and the levels were engineering, accounting, marketing, and what was the last? Production. So these are the levels. So an independent variable could have multiple levels. Now, this is one way because it looks at one variable and it has several levels. A two-way ANOVA would actually have 2 variables. So instead of just the IV of departmental evaluation, we could have another IV. Let's say gender. Gender would be another IV. Like maybe engineers who are men are more satisfied than engineers who are women, while let's be sexist. Well, maybe on the other hand, marketing women are much, because marketing involves interaction, and women like interaction, human interaction, while engineers are just sitting and playing with their toys. And that's what men like to do. So what would the levels be for gender? If you had gender? Male and female. Very good. Okay. Sorry?
You put transgender in there just to be
right. If you want to do that, if you in your sample have transgendered, you would include that. Okay. So you have now 2 IVs, and this would be a two-way ANOVA, meaning you have 2 IVs, and you're looking at the relationship between these 2 IVs and their impact on satisfaction. Now, what's interesting, we're not going to do any calculation with two-way ANOVA. But I'm going to teach you how to analyze it, or how to look at the data, because you're going to, at some point, be reading something in research. And basically, you can think of two-way ANOVAs. So let's keep this here. Let's erase this. In terms of a two-way ANOVA, it could be divided like this. This is engineering. This is marketing. This is production and accounting. And you can see you can have cells. And this is male, and this is female. This is called a factorial ANOVA. Factorial meaning that you have more than one factor. And factorial ANOVA are typically called, like this is a two-way ANOVA. This would be actually, technically, it would be called a 2, because you have 2 levels of one variable by 4. This would be called 2 by 4 ANOVA. And what you would do is you would do the calculations for an F. You would calculate an f, but it'll be much more complicated than what we've done. Well, more complicated than what we've done. And you would get in each of these blocks an actual mean. So the mean for males in engineering will be something. Let's say the mean would be 3.6. The mean for females in engineering would be 0.6. Mean for males in marketing will be 5. Males for marketing here would be 5. Production, let's say, is 3. Production is 3, and accounting would be, let's say, 0.6, and here 3.8. Okay, so these are the means. Let's say you get such a distribution of the means. Okay, what's really interesting about a factorial ANOVA is you can start looking at something called an interaction. In addition to just looking at, hey, do males and females differ? You can ask the question, do males and females differ on their satisfaction? And all you need to do is get the average for males. Let's say I mean, I'm not going to calculate it, but let's say the average for males ends up to be 3.8. Average for females ends up to be 3.8. Hey, males and females don't differ. They're both 3.8. Maybe let's make this 3.7. This would be the average of all of these. On the other hand, you might discover also, let's say you could have this. You could have this scenario. Let's say your mean for this one is 4.2, 10, 6, and 4.4. Well, here you can see that there's no difference between male and female, but there's a difference in which department you're in. So you can see there's a difference in department. But is this difference just across departments regardless of whether you have a male or female? And what you test now, see, we learned how to test this, right? We just did, in fact, something very similar to this. We just compared the average on marketing, and we didn't take into consideration male and female. We ignored male and female. We ignored this, and we just said, are these values different? However, maybe there's a difference between males and females. So you add this variable, and you discover that really there isn't a difference between them here. There's a difference here, but within the cells, they're actually different. So you see here, males are much more happier as engineers, while, so higher numbers are happier. Males are much more satisfied as engineers, while women are much more satisfied as accountants, and they're least satisfied as accountants, males, and females are least satisfied as engineers. So there's an interaction. This is what we call an interaction effect, meaning that depending on whether you're male or female, you might actually be more satisfied in one department versus the other. Everybody see that? This is called an interaction. Yes?
Will this be on the test?
Yes.
Can you repeat interaction?
An interaction is when actually let's use the book to give us the full.
Is this still chapter 10?
Yeah, this is still chapter 10. I'll give you the page in 1 second. So if we go, always open to the glossary. Interaction effect is a situation in a factorial analysis of variance in which the combination of variable has an effect that could not be predicted from the effects of two variables individually. Okay, so let me show you this, Arian, if you pay close attention. So if you look at this alone, or you look at this alone, this is not enough for you to tell, oh, males are more happy in one department and females are more happy in another. Okay, that you only could discover if you do a factorial. And that's what this definition means. Situations in a factorial analysis of variance in which the combination of variables has an effect that could not be predicted from the effect of two variables individually. Like if you simply took this You couldn't predict that females are more happy in one profession versus the other, or one department versus the other. And if you took only this, you can't predict. It's only when you do a factorial analysis can you predict. Everybody with me? OK, the other continuation of that definition is the effect of one grouping variable depends on the level of the other grouping variable. So the effect here is dependent. So the effect of engineering is dependent on whether you're male or female. If you're male, you're much more likely to be satisfied than if you're female. And if you're female in accounting, you're much more likely to be satisfied than a male. So you see, one effect is dependent on the other. So you need to do that to test for interaction. How do you look for interaction? You look for interaction when you have these cross differences among the relationships between variables. Let's actually do an exercise together. You look for an interaction by looking at actual cell means and differences within cell means. You know, these are called marginal means, Arian, if you look here. So these here are in the margins. So these are marginal means. They give you main effects. They give you the main effects, the main effect of department versus the main effect of gender. But to look at the interaction, you have to look at the cell means. And to answer the question that I was just asked, where are we reading this stuff? It is on page 434, 343. Becoming dyslexic. It's late at night. It's the same for you. I see people nodding off too. So here we go. Page 343 says identifying an interaction effect in words and numbers. And you can see in the second paragraph under that, you can see an interaction effect numerically by looking at the pattern of cell means. If there's an interaction effect, the pattern of differences in cell means across one row will not be the same as a pattern of differences in cell means across another row. Everybody with me? So look at this. So across this row, the pattern of differences is different from this row. This row here, this is higher and this is lower, while this is higher and this is lower, and this is lower and this is higher in this other row. You can see they're flip-flopped. Everybody with me? And that's how you detect an interaction. You could also draw it out. It's nice to plot things out. And typically, an interaction plotted out as a graph like this. Let's ignore this for a second. Let's ignore here. Let's ignore this for a second, OK? So act like this doesn't exist for a sec. And let's plot this as if it was a 2 by 2. If we ignore these guys, we would have a 2 by 2 ANOVA, meaning you've got only two levels of one variable, engineering and accounting, and male and female. This would be a 2 by 2. If we plot it, we can plot it as a graph. Let's say male and actually, let's do engineering